Welcome again. Now we will discuss about the principal component analysis. So, principal component analysis is a dimensionality reduction technique. So, dimensionality reduction technique means where you're going to reduce the dimension from, let us say, three-dimensional to two-dimensional and two-dimensional to one-dimensional. Okay. So, what are the advantages by doing this? Okay, if you go ahead and search the advantage, why, if you can directly search as why PCA is required, is used in machine learning, let us say. Here you can see dimensionality reduction, obviously simplifying the data sets. We are going to transforming them into a smaller set of uncorrelated variables. Okay, dimension, the feature scaling we can do, data preprocessing can be done, overfitting can be reduced, multicollinearity reduction, noise reduction will be there, computationally it is efficient. And if you want to go ahead and plot them, okay, sometimes three-dimensional data you cannot plot them. You can use PCA to reduce it to two-dimensional and then plot them. Okay. So, for example, in k-means clustering itself, how can you use the PCA means? Here in our example, we only have two different columns only, age and income. Let us say there are five columns are there. Okay, and then I wanted to plot the five different columns. I have clusters, but here two columns means x-axis and y-axis you can take and present it. But if five different columns are there, I cannot use a two-dimensional plot to plot that, right? So for that, in that situation, data visualization also it will help. PCA will help to reduce that higher dimension to the lower dimension, so that five columns into, let us say, like 3,000 rows and five columns are there. Instead, we can consider two columns. Okay, one is for X and one is for Y, and again 3,000 rows or 300 rows, whatever it may be, or 30 rows. Rows is not going to be changed. Columns going to convert that 5 to 2. Then how it is possible? See, we cannot reduce like that. We have to reduce in such a way where the pattern, mathematical pattern or mathematicality should be same, right? I hope you got my point. For example, let me go ahead and take the new slide, PCA. If you are doing PCA means, let us say these are the data points. So you are having, X1, X2, X3, X4. These are the points. These points I wanted to plot it here. Every point is important. I cannot plot them in two-dimensional, right? I have to use maybe three-dimensional, where I have to consider the plane instead of line to plot them all. But if I wanted to plot you can use PCA concept, means principal component analysis. It is dimensionality reduction. What it will do is it will understand the mathematical pattern between 4 points. Okay, it will not miss out the relationship. Okay, it will not miss out the relationship, and it will not. I mean, means here covariance. It will not miss out the covariance. It depends on the covariance actually, and it will plot that in two dimension. For example, here are the points, and it will convey the same thing even if you go ahead and plot in 3D or 4D. Got it? So, its main concept is to reduce the dimensions. Okay. By doing this, these are the things that what we can achieve. Okay. Okay, then question is how it is possible to reduce the that dimensional to the lesser dimension? Here we have to follow some steps to do that. Okay, here we have to follow some steps to perform. I mean to do that. Those steps now we can discuss. Okay, so PCA steps I can write it as, yeah. PCA steps. So these steps has to be performed one by one. First step is data set. So now what we are doing is we are now doing two-dimensional to one dimension. Okay. So same procedure has to happen from 3D to 2D also. Okay. So first data set, let us consider this is what my data set X and Y. Some points are there 2, 3, 4, 5, 2, 6, 4, 2. Okay. I have to find out step 1 is covariance. Covariance matrix. Matrix. This is the first step. So how do we do covariance matrix means covariance of x to x, then covariance of x to y, covariance of y to x, and covariance of y comma y. Of course, these two values are same. If you find out the covariance between x and y, same as like covariance between y and x, right? So that is what Maria has a question last time. What can be decided as x? What can be decided as y? Obviously, both are same because the covariance itself is same. Maybe you may have the representations different, okay, by choosing different values as x and y, but you will get the same information, okay. So covariance, this is what the covariance matrix, okay. So once you calculate this covariance, this is what the covariance matrix. Again, how do we calculate covariance of x comma x? I will explain you one covariance, same way you can do it for others, okay. This is simple mathematics. For example, if you wanted to find out covariance of x comma x, then simple formula summation of x minus x bar into x minus x bar divided by n minus 1. For example, in this example, how many n means total, how many are there? 4 points are there. Then here we will get 4 minus 1 is 3, denominator fixed. Okay. And how many, what is the value like x bar? X bar is simply mean 2 plus 4 plus 2 plus 4 divided by 4. 6, 6, 12 divided by 4, that is 3. Okay, this is what the x bar, right? So this is what x bar and into. And what is this x minus x bar means? See, first point is 2. So 2 minus 3 into 2 minus 3 plus remaining points 4 minus 2 minus 4 minus 4 minus 3 whole square. Obviously, these are squaring only, right? That is why directly I'm using square. And again, 2 minus 3 whole square plus 4 minus 3 whole square. This is the way how I will get the covariance of x comma x. Similarly, covariance of y comma y also same summation y minus y bar whole square divided by n minus 1. And covariance of x comma y is equal to covariance of y comma x. This formulation is little bit different. X minus x bar into y minus y bar n minus 1. Here earlier we have both parameters are same. That is why x square came. Now we will have xy. That is why the relation is like this. If you calculate all such things, x, xx, xy, and yx, and then yy, then all put them in one particularly. Okay, so that you will get covariance matrix. Let us say, let covariance matrix is 0.61. I am just randomly selecting, okay, 0.61, 0.61. Here I will use 6, 615, 615, 0.7166. This is covariance matrix. This is step 1, covariance matrix. Then step 2 is we have to find out the eigenvalues. Eigenvalues. In your childhood or else in your class 10th or plus 1, plus 2, any any time in your mathematical journey of your, I mean, any time in your educational journey, you might have came across this eigenvalues, right? So now you will understand what is the major part it will, do. We have to calculate the eigenvalues of this covariance matrix. If you forget how to we calculate, means simple C minus lambda I is equal to 0. C means this particular matrix, simply 0.616, 0.615, 0.615, 0.716 minus lambda into 1001. Obviously, I is identical matrix. 2 cross 2 means it is also should be 2 cross 2 equivalent to 0. So this particular value minus lambda times of 1 is equal to 0. That way we have to write equations, right? So that we will get, if you do it, then two two eigenvalues we will have. Obviously, we can see 2 comma 2 matrix means 2 eigenvalues we will get. That is why it will have a quadratic function. If you do the multiplication, you will get to know this value minus lambda of this plus again this value minus lambda of 0 equal to 0. And second equation is this particular value and again this and this. You will do it, then you will get this. Okay, lambda square minus 1.33 lambda plus 0.063. I already calculated with the basic values. That is why I'm getting these values. Okay. For this class, I already calculated with calculator and mathematics. Okay. Once you get this quadratic equation, let me write it here. Lambda square minus 1.33 lambda plus 0.063 equal to 0. Then you know how do we find lambda 1 and lambda 2, because two lambdas are there. So you have to find out lambda 1 and lambda 2. Let us say lambda 1 is equal to 0.04, lambda 2 is equal to 1.28. Okay. Once you get the lambda points, that is step 2. Step 3, obviously, what we will do with the lambda values, we will find out lambda, so eigenvalues. What we will do with the eigenvalues, we will find out eigenvectors. Eigenvectors, right? Eigenvectors means C V1 is equal to lambda V1. Here V1 is the one is stands for eigenvalue 1, eigenvalue 2, C V2 is equal to lambda V2. This is eigenvalue with respect to eigenvector. So here you can decide which is the maximum value. For example, here this is the maximum value that I can choose. Lambda 2 is what my value. So I can find out only the eigenvector 2. Got it? So it is your choice. Like for example, if you are having two-dimensional data, then you will get two eigenvalues and two eigenvectors. Your intention is to convert to one-dimensional, right? Then you have to choose one eigenvalue and one eigenvector. Here I am choosing the maximum value. So that is why I am choosing this one. Got it? Okay. 0. Sorry. Yes. Maximum value only. Yeah. Got it. Is that clear? Up to now, is this clear? Step 2 and step 3? Step 2 and step 3, is that clear? How do we find this? So C already we know 0.616, 0.615, 0.615, 0.716. This is C. V2 means simply x2, y2. Lambda value we know that 1.28 is what I'm going to consider. Okay, this is the biggest value. And V2 again x2, y2. I have to find out this x2, y2. If you find out this x2, y2 point, so let us say you will get the x2, y2 point as, that is what we do as 0.67, 0.735. And this is what we called as principal component. Principal, principal component. So this is what principal component. So basically, if you are converting 3D to 2D, okay, then three eigenvalues you will get, three eigenvectors you will get. You have to choose two eigenvalues and two eigenvectors. Those two eigenvectors are called principal components. Got it? Up to now, is this clear? How do we get the principal component? Is that clear? Can I get a quick confirmation? Is that clear? Hmm? Is that clear? Okay. So last step, once we get all eigenvalues, eigenvectors, and then we decide the principal component. Once we get the principal component, that is V2, then what we will do? How still did not get the one dimensional, right? We only got the V2. Simply it is a point. This point is simply 0.677 and 0.735. That's it, a point. We yet to get the single dimension. So you remember that this is what the the data points, right? 2, 3, 4, 5, 2, 6, 4, 2. So you have to take this data xy means as a form of vector. So what are the points? 2, 3, 4, 5, 2, 3, 4, 5, and then 2, 6, 4, 2, 2, 6, 4, 2. These are the points. I have to multiply with this particular 0.677, 0.735. If I do the multiplication, this is what we called as F star of V2. F represents the data set. We represent the optimal principal component value. If you do this multiplication, this is simply 4 cross 2, 4 rows and 2 columns. This is 2 rows and 1 column. So these two are equal, right? I can do multiplication, right? The updated value what we get is 4 rows and 1 column. So 2 times of this plus 3 times of this, you will get one value, right? Another value, another value, another value. So these 4 points are the one dimensional points. Okay. So two dimensional getting converted to one dimensional. You can see two dimensional got converted to the one dimension. This is the way how principal component analysis works to do the dimensionality reduction. If you have two different V1 and V2, V1, V2, we will give V1, V2. Then accordingly, three-dimensional will get converted to the two-dimensional then. Okay. So then how do we plot that? Okay, we understood that this is the way, but how do we plot that? Plotting happens like this. Let us say your points are like this. And you know that how we are calculating the eigenvalues, right? So we have to plot the eigenvalues. For example, eigenvalue, let us say this is V1 and V2 vectors, eigenvector V1 and V2 points. So if V2 point, V1 point we have, so we have to draw the line, draw the line like this. If you are choosing V2, then estimate all the values on only V2 and plot on V2. If you are choosing V1, then plot all on V1. So that is the way how do we convert the two dimensional to one dimension. Anyway, I have a very nice representation. Let us implement the same things. So let me repeat you again the steps. Steps are very easy. First, the data set. Second, covariance matrix. We have to find the eigenvalues of covariance matrix. Then once we get the eigenvalues, we need to find out the eigenvectors. If you are converting to the single dimension from two dimensional to one dimensional, then choose the largest eigenvalue and representative eigenvector. Okay. So use that particular eigenvector, and with the help of eigenvector, you have to multiply with uh, the input data set. Then you will get the output as a dimensional reduction matrix. Okay, that matrix actually, if you plot, all the points will get converged and then will form into a single dimension. Now let us see how it is going to do, going to work. Here you can see 2 comma 1, 3 comma 4, 4 comma 2, 5 comma 5. Some random data set I considered, two dimensional it is. You can see two rows and two columns are there, two dimensional. And first point is covariance matrix. Calculate mean, first of all, obviously. With help of mean, I can calculate covariance matrix. See covariance matrix. After covariance matrix, then I need to find out the eigenvalues. These two are eigenvalues. Then eigenvectors. These two are eigenvectors. Once I get the eigenvectors, then my goal is to find out the principal components. Okay. So how I'm doing is, see, you can see here I'm doing the sorted one and I'm getting the largest value, and accordingly I'm calculating the principal component. Largest one, which is having the largest one, that particular point only I'm taking as a principal component. This is the first one is the largest one when compared to the second one. Here you can see and observe. That is why I'm choosing the largest values as representative. See, the first point representative. This is the first eigenvalue, largest eigenvalue. That is why the largest eigenvalue representative vector only I'm taking. This is what the principal component. If I do the multiplication with the current data set with this point, then I am getting, see, this is what the transformed data. I'm just doing the dot product. I already mentioned you, dot means you will get the matrix multiplication. This is what the one dimensional data. If you go ahead and plot them, okay. So here you can see this is the initial data points. Now PC1 or PC2, which is the principal component. For example, PC1 is what principal component. Then accordingly, instead of two dimensional, in one dimension, you can see all the points are arranged in single straight line following this line. Okay. So this is the way how I got just converted the two dimensional to one dimensional. This is the way how PCA works. Okay. Here you can see the transformed data points. In reality, how we do it on data set means you can see PCA is available in decomposition in scikit-learn library. So you can use PCA from there. This is what the data set of iris data set. This is how it will looks like sepal with petal with target species. If you want to scalar, standard scalar or normalized scalar, min max scalar, anything you can use. Here I just used a standard scalar, and where mean is equal to 0 and standard deviation is equal to 1. I already discussed this thing in mathematics class, and like I just implemented and then got the scaled values. Then what we are doing, covariance, eigenvalues, eigenvectors, all got calculated. This is manual. I mean, if you want to build your own algorithm, this is the way. But if you want to use the predefined one, then scikit-learn, from scikit-learn, you can see the PCA is available in decomposition models. So you can just call the object of that and then fit transform of scaled values. Then you will get the principal component values. You can decide the first one and then you can plot all points in one. Okay. So out of this particular thing, I just used this one to plot. Got it? So this is the way, and the correlation matrix with respect to PCS. And here I provided the extra information like the building of the algorithm. If you wanted to build your own algorithm, this is the way. Okay. And here you can see this got converted to first two principal components to scree plot. Okay. This is all about principal component analysis. Okay. So let me stop here.